Okay, welcome back. This is projectile motion for AP Physics C. You guys have all done this before. You're all kind of pros at it. I've got an example problem up here, and basically it's a problem that you guys have done. In my work, I kind of split my work into an X side and a Y side. All right, so we've got an X side and a Y side. When it comes to projectile motion, what's the most important idea or set of ideas? Watch my keys. What happened? Why? Gravity! Okay, good. We're getting somewhere. Tell me about gravity.
It's constant.
It's constant. What's that mean?
It means that it's not going to change in terms of your acceleration.
You mean the acceleration is constant. What's its value?
9.8.
9.8 meters per second squared. Down. Down! Gravity points down, yes? Does gravity ever pull things sideways?
No.
Depends on how you look at it. Okay, so a ball's on a ramp. Does gravity pull things sideways?
Yes.
Well, wait. Wait. Now we've got a disagreement going on. You say yes, the gravity pulls the ball sideways. You say the movement is sideways, but
Gravity is still down.
gravity's still down. Which is it? Right. The normal force is the thing that's actually pushing sideways. Gravity itself always pulls down. All right. Very, very important concept. And for beginners in physics, that's kind of a big major idea. They're like, oh, the reason it pulls down, it goes sideways is because gravity pulled it sideways. No. Gravity does not pull sideways ever. In fact, I would argue that the definition of the word down is what?
Which way gravity points?
The way that gravity pulls things. Got it? You mean other forms of gravity pull things sideways?
Other planets' gravity.
Didn't Newton explain gravity
Other
as...
objects. They also have gravity. Every object has gravity.
Yeah.
That's math, but it's gravity.
Okay, so again, I would argue that if you're going to define a downward direction, you're going to define it in the direction that gravity pulls. Right? So down with respect, if you're standing on the surface of the sun, not that I recommend it, which way would down be? Down towards whatever way the sun's pulling you. If you're standing on a planet, likewise. Yes?
Is it true that Newton explained like how planets orbit as just a constant falling while they're moving sideways?
Yep.
Because that's how it was in the movie, and I'm not sure if that's how he actually explained it.
Which movie?
The Newton movie. I can't remember the title.
The Newton movie.
That's good.
That sounds like a great movie. I'm not familiar with it. But yes.
If I remember the title, then I'll...
Yeah, we can talk about that when we get to planetary motion. It's actually, we've got a whole big long section on it that's more than what you did last year by a little bit. Actually, by a lot. Because you did it as part of circular motion, and it was just a very quick thing. You're like, planets go in circles, and that's it. That's pretty much it, right? We're going to go in a lot greater detail this year. But I think I'm going to punt that until we get there. But yeah. Okay, so anyway, down. Yeah, important ideas. Gravity only pulls down. Down is which direction? Is it X or Y? Y, in the negative Y, right? Okay, gravity only pulls in the negative Y direction. So what direction doesn't gravity pull? The X direction. So if you've got something in free fall, how much acceleration is there in the X direction? 0. And how much acceleration is there in the Y direction? Negative 9.8 meters per second squared, or 9.8 meters per second squared down. I suppose you could define the positive y direction to be down, but that would be a little goofy. All right, so, and typical projectile problem, you take a projectile, launch it at a 30-degree angle, speed of 20 meters per second, off of a 15-meter tall cliff. You know, you get a triangle like that. And you can look through this problem. It's in your notes. You probably did a million different versions of it last year, but whatever. Question. If you launch it at 20 meters per second, what is its initial launch velocity vertically? What's the vertical component? Can anyone do that in their head?
20 sine 30.
20 sine 30, what's that? It's actually 10. All right. And what about the horizontal component? 10 root 3, which is, any guesses? 17 point, how much? 3? How did you get that? Yeah, right. It's you know, cosine of 30 times 20. Okay, good. So you guys are all smart. You all know how to do trigonometry. Let's move on. Okay. Let's change the question up a little bit. Let's assume that I gave you the horizontal velocity as a function of time and the vertical velocity as a function of time. What would the horizontal velocity as a function of time be in this problem? 17.3. Are we missing anything? Nope. Why not? Shouldn't it be as a function of time?
But it doesn't change.
It's constant, right? So it's just constant, constant speed. Okay, what about vertical? Does that change as a function of time?
Yes.
Yes. How?
There's acceleration.
Okay, so how much is that? 9. Okay, so if positive direction is up, what would the equation for vertical be? Vertical velocity as a function of time is equal to what? Negative 9.8 t plus the initial velocity, which was 10. So the initial velocity was 10, and this should be a 9.8 instead of a 10. Sorry, I was in regular physics mode when I wrote this. Regular physics, we used negative 10 rather than negative 9.8. Does everybody see how that equation works? All right, so we got an x velocity and a y velocity, both as a function of time. What if I said, I want you to solve for the position as a function of time of each of those? What would you do? You'd integrate. Okay, so you do your little integration thing. And you do that, and you end up with these equations. Those equations are the position as a function of time of x and y. And does everybody understand the x equation? Is that a linear equation? Yes or no? Is it a straight line? Yes or no? Yes, that is a straight line.
Oh,
Yeah, because 20 cosine 30 is just 17 point something. What about the y equation?
It's a parabola.
Why is it a parabola? How do you know it's a parabola? Because there's a t squared in it, right? Is it a smiley parabola like this or a frowny parabola like this? It's frowny. Why? Because it's negative. All right, negative is frowny. Okay, what's this plus 15 right here? Initial y position, also known as how high you launched it from, is 15. Okay, so it goes in the y goes up and then down, starting from a height of 15. Okay, good. Now that's all fine and dandy. What if I said, I don't care what the x equation is and what the y equation is. I want a total equation that I can use to compute the trajectory of the projectile. What? What is a trajectory?
Path.
The path. I want to know where the projectile is. Well, actually, no, I don't really want to know that. I would want to know what it looked like if you did a strobe photograph of it. Right? What shape should it make? Parabola. I want to know the equation of that parabola. Could you do it?
Yeah.
Okay, if you can do it, what's y a function of? What's on your vertical axis? Height. What's on your horizontal axis? Distance sideways. In other words, your vertical axis is y, and your horizontal axis is x, and you're creating an equation, y, as a function of x. Have you done this before? When? In Algebra 2. It's called solving equations parametrically. All right? You've got a y equation as a function of time and an x equation as a function of time. And what kind of equation are you trying to create? Y is a function of x, and how do you do it? Yeah, you get rid of the t, right? You solve one of your equations for time and plug it into the other one. So that's what we're going to do. All right? Solve the x equation for time. You get t equals x over 17.3. Plug that into the other one, and you end up with this one. Negative 1/60th x squared plus something times x plus 15. Is it smiley or frowny?
Frowny.
It's frowny, and this is what it looks like. Hey, guess what? If you took a picture of this projectile as it was flying through the air and threw it up on a grid, you'd get that shape. And it should match up, assuming there's no air drag. Sound good? All right, so that was your warm-up. It's your nice introduction to projectile motion. You did all of this stuff last year, I think, other than maybe the parametric stuff. Okay, but the basic idea for parametric is you want a y as a function of x, and you're given as x as a function of t and a y as a function of t. Okay, fine, let's move on. I said when we first came in that AP Physics C we're going to get rid of numbers. This equation is nice and handy and convenient and short because it's got numbers in it. We're going to take this equation and make it generally applicable to all free fall motion, because there's going to be no more numbers in it. It's all going to be in terms of launch velocity, launch angle, launch height, and what else am I missing? What else would affect the motion? Gravity, G. All right, so here we go. All right, in general, the kinematics equations are, what's the horizontal acceleration for free fall? 0. And therefore the horizontal velocity is just going to be your initial velocity, and the horizontal position is initial velocity times time plus wherever you started. And likewise with the vertical, what's your acceleration? G, down. All right. And 1/2 gt squared plus v naught vertical, your initial vertical times t plus your initial vertical height. Fine. We all know this. We can determine a general function for the trajectory of an object just by using these two position equations. All right, what do? We got to get rid of the t, right? So how are we going to get rid of the t? Solve. And then substitute. You do that, you end up with this thing. Who here wants to memorize this? Raise your hand. Right, I love the enthusiasm. Do not memorize this equation. That would be a complete waste of time. On the off chance that it shows up on the AP exam, you can derive it. All right, but what does this equation basically say? Y as a function of x. Agree? This is the equation of some parabola. Why is it a frowny one?
Because gravity's on this thing.
Because it's negative. Oops, that went away. What's this value right here? That's why not. Right? Anything else of interest on here? What's this value right here? That's x naught. It's not. Sorry. Child humor. This is going on the internet. All right. Okay. That's a big ugly equation. And to be honest, I don't know that anyone's ever going to use this. So we can actually make it somewhat useful if we simplify it. Say, for example, what if you had a tennis ball cannon? Now, raise your hand if you've ever seen the thing fire. Okay, it should be everybody, right? When you shot the tennis ball cannon, what height did you shoot it from?
Just about a couple feet above the ground.
Ground level-ish, right? What height did it land at? Ground level, pretty much, right? So if you assume that the launch height and the landing height are the same height, what happens to this equation? Do you see it? What's true about this y and that y? They would be equal. In other words, they would cancel, right? So this whole thing, it would be 0 over here plus whatever was left in the middle. Also, if you're talking about how far something goes from start to finish, what would the total change in x be? Distance that it traveled. So this x minus delta x here and here, guess what? We're going to call that distance in the x direction total, right? I'm just going to call it dx. Sound good? Or you could call it delta x. I don't care. Something. How far it goes in the x direction. So we got 0 for the y's. We got delta x's for the x's. And all that's left over is what? An initial vertical velocity and an initial horizontal velocity and gravity, acceleration due to gravity, right? So we're making this simpler. All right, so here we go. Did you know that you can actually relate the horizontal and vertical velocities initial?
Yeah.
How?
Trigonometry.
With trigonometry, right. We're actually, instead of writing horizontal and vertical velocities, we're going to write it as initial velocity and the angle. So, the initial horizontal velocity is how much? The initial velocity times cosine. And what's the initial vertical?
Initial height times sine.
Initial times sine. So if you got initial vertical over initial horizontal, that means you've got V naught sine over V naught cosine. What happens to the V naughts? They cancel. And you're left with sine over cosine, which becomes tangent. All right? Good so far? So now we got an equation that looks like this. We got negative 1/2 g over your initial velocity squared times cosine squared times the horizontal distance squared plus tangent theta times the horizontal distance. Now, I say, wouldn't it be cool if we could solve this and figure out how far the tennis ball ought to go. Could you do that?
But wouldn't you take in factors like spin and things?
We're going to forget about air. We're going to pretend we're doing this on the moon. Right? Could you solve this equation for how far it should go? What would that look like? Well, it would look like this. Well, let's see. I'm going to skip. We're going to take this. What's in both terms here? Dx. So we're going to pull one of these dx's out front. And wait, it's equal to 0. Wait, hold on. Dx is equal to 0. Does that mean it's going to go 0 distance? No, how come there's a dx equals 0 here?
There's two solutions to that.
There's two solutions. Why?
Because at initial, it's touching the ground, and at the final.
Yes, at the initial distance, it's got a height of 0. And at the final distance, it's also got a height of 0. That's why there are two answers. All right? So we're just going to look at the second answer, which is more interesting. All right? So we got negative blah, blah, blah times dx plus tangent theta. Sound good? All right. So dx equals sine over cosine times all that blah-de-blah. If you cancel out the cosines, you end up with... Okay, if you cancel out the cosines, you end up with a 2 times a sine times a cosine. You guys remember that trig identity? What is it?
Double angle.
It's the double angle at sine of 2 theta, right? So you end up putting those sine and cosines together, and you end up with negative v naught squared over g times sine of 2 theta, which is pretty freaking cool, because it's a very simple, short equation. This is known as the range equation. Has anyone ever heard of it before? No? Okay. And I think you guys, if you took an engineering course, you might have heard of it, but yeah. Basically, what does it say? It says, well, what's the distance depend on? What does the distance depend on? How fast you launch. What else? The angle, and what else?
Gravity.
How much gravity there is. Does that make sense? Okay, so question. If you are... Does anyone in here play a sport? What do you play?
Water polo.
Water polo. Bad example. Outside field sport, yes.
Oh, it's not outside. Badminton.
Badminton, too much air drag, yeah. Baseball. Okay. What position do you play? Shortstop. Okay, so not an outfielder. Okay, so if you had somebody who threw a ball at 40 miles an hour versus somebody who threw a ball at 80 miles an hour, how much farther should the 80 mile an hour thrower be able to throw the ball? Velocity squared, right. So, how much farther? How many times farther? 4 times as far. Why? It's squared velocity. If you throw the ball twice as fast, it's not going to go twice as far. It's going to go 4 times as far. Got it? What about if you throw it 3 times as fast? Little kid who throws at 30 miles an hour versus somebody who throws at 90 miles an hour. 9 times as far. Kind of an interesting result. Anybody have any idea why that is?
Because gravity isn't directly pulling on the...
Yeah.
Well, it's pulling it down so that it falls faster, but it's not pulling directly against the way that you're throwing it, right? Your throwing motion is more horizontal than it is vertical if you're throwing for distance.
the difference is time.
Wouldn't it be
Okay,
like-
Stephanie says time has something to do with it.
Because it
wouldn't it be
takes.
Why, if you throw 3 times as fast, does it go 9 times as far?
Because it's squaring the amount.
I know because it's squaring the amount, but somebody give me a conceptual reason.
It's in the air longer.
It's in the
Oh, I'm
air.
just kidding. No, it's
You
not.
yes,
Is that
go.
right?
Yeah, absolutely. Go with that thought.
It's in the air longer, so it's not in the air longer.
It is in the
It is because you throw it faster, so it goes against gravity more, so it goes higher.
Oh, are you
or
throwing it
starts
up?
falling.
Yes, if you don't throw it up, it's not
Okay,
going to leave the
I thought
ground.
you were like throwing a baseball pitch.
Well,
It's still
okay. Assume again. This range equation assumes launch height is equal to landing height. So if you throw it horizontally, it's never going to leave the ground.
Right. Okay.
Yeah. So why will it go 9 times as far as if you throw it 3 times as fast?
Goes to larger heights, and so time is double.
Time is just larger.
Times bigger, and say you throw it at a 45-degree angle.
Oh, wait, because you're increasing the y velocity so it stays up longer and the x velocity so it travels farther?
Yes! Yes, the x velocity, if you throw it 3 times as fast, is going to be 3 times as much, right? So it's going to cover horizontally 3 times as fast. Also, the y velocity controls the time in the air. So if you triple the y velocity, you triple the time in the air. Now you're tripling the horizontal speed and tripling the amount of time that it spends going that speed horizontally. Overall, you got 9 times the amount of time in the air. Or sorry, 9 times the amount of horizontal distance traveled. Does that make sense? That is why it's launch velocity squared. Does it make sense? All right, cool. What about gravity? If you did this on the moon where gravity was 1/6 as much, what's the effect going to be? It'll stay in the air how much longer? 6 times longer, right. So that's like, you guys saw the pictures of the guys doing the moonwalk, they're like, right?
That was perfect.
I know, that was beautiful. I do what I can. Were they just faking it, or was that real? There were wires holding them up. No, they were just taking normal steps as far as they were concerned, but what happens to the distance they travel? 6 times as much. Right? So a little what they meant to be just like a normal step ends up going 6 times as far. Sound good? And you can probably measure that if you look at the video. See what their step would have been on Earth. Last one. It also depends on launch angle, right?
Yes.
So the question I have for you guys is, at what angle? No, different question. When is sine theta maximum? This is a math question. When theta is 90, right? That gives you sine theta is 1. So when is sine 2 theta maximum? 45 degrees. So when is distance traveled maximum? 45 degrees. Raise your hand if you've done this before. All right. Does that make sense? All right. That's why 45 degrees is the optimal angle, assuming no air drag. Okay. So here's a question. Why are 20 degrees and 70 degrees complementary? Meaning, rather, that was a bad question. Why will a projectile launched at 20 degrees go like this, and 70 degrees go like that and land in the same spot? Yes.
Because one that's 20 degrees, it'll have comparatively less y velocity than the x velocity, so it won't go as far. And then the one that's launched at 70 degrees, it'll be like flipped. The y velocity will be much greater, but the x velocity will be smaller, so it'll still go the same distance.
I like that conceptual explanation. Can you give me a mathematical one?
Sine 2 theta for both 20 and 70 are the same thing.
Oh yeah, sine of 2 theta are both 20 and 70 are the same thing. I agree with that, but there's an even simpler explanation. Look at this one and look at that one.
Sine,
Do you see it?
yeah, the sine of 70 is the same as the cosine of 20.
Right. The sine of 70 is the same as cosine 20, so it doesn't really matter what order you write them in. Which one you pick. You're always going to come out with the same answer. Good? All right, so there it is. In a few days, we're going to talk about air drag. And when we talk about air drag, we're going to see how all of this goes out the window.
Yes.
All right. And I would love to launch out the window, except for our windows don't open. And that would be a problem if we actually did.
Can we go out in the football field and launch them?
We might have to.
Outside?
So, but before we do all that, since we're kind of on the topic of launching stuff, what is the optimal launch angle for the tennis ball cannon, assuming there is air drag, because there is?
You want to go lower than 45.
Okay, well, let's do this as a vote. Who says that the optimal launch angle is more than 45, like, say, 50? Who says the optimal launch angle is less than 45, say, like 40? Who says, no, the optimal launch angle should still be 45 degrees? Would anyone care to argue?
Well, if you shoot it with a greater y velocity, then it's going to spend more time in the air, which will give more time for that air to drag on it.
So you're saying if there is air drag, we should take a trajectory like that? Does anyone disagree with that? So greater than 45 will give you more time in the air, and therefore it should go farther, right?
No. That's not what he said. He said there's more
Yeah.
air drag the longer you're in the air.
There's more air drag the longer than you're in the air.
So you
Okay.
go shorter.
So you should go do something like this? Huh. Does anyone have a complete argument?
You do.
Because all I heard about was time in the air, but not necessarily about distance traveled.
Oh, and when you have it going closer horizontally, then you have a greater x velocity, which will add to the distance.
But it's still, yeah.
Greater x velocity, so it takes longer for the drag to stop it.
Gravity still will.
'Cause, like,
So it's going to take more. It's going to spend more time slowing down if it's got a greater x velocity.
to slow down to the same velocity x, y is the same.
So it's going to take more time to slow down.
Yes.
The same velocity.
Well, lower arrows don't
So it's going to. So if you shoot it lower, it's going to spend more time in the air.
No, it's
No, it's
one is probably
That doesn't make sense because we all know that time in the air depends on on vertical velocity, not on horizontal. Huh. What? Here's a hint. What way does air drag always point?
The direction.
against the direction of
Or against.
Backward, right. Whatever direction the ball is going at that particular point in time, it's pointing the other direction. Yeah, go ahead.
So in that case, I'm going to say that air drag affects the x and the y velocity in the same way.
I
So that's
totally
45.
disagree. Totally disagree. See, if the ball is right here, what way is air drag pointing? Mostly up. If the ball is right there, what way is air drag pointing?
to the side.
Kind of left and backwards, but more left than backwards, right? So air drag direction changes throughout the trajectory. So I still haven't heard a good explanation. We all are coming to the conclusion that it's better to launch at a lower angle, but why?
Because you drew it that way.
Because I drew it that way. That's right. I drew it that way for a reason. Because that's what it actually looks like. But why?
Because
That's
the
the way it
direction that it goes in, the air. Since the air drag is pointing backwards, you're slowing down the ball to the point where it just kind of almost stops in the air and it just falls down. So you want to have it going.
Yes.
Is it,
Yes.
I
Yes.
almost
Yes.
have-
Yes. It's almost you're almost there. Yeah. Go ahead.
No, I mean, like, are we talking about this way? Like, pushing. Oh, never mind. I was thinking with my hands.
Wouldn't you agree that after a certain period of time, the ball's just going to slow down?
Yeah.
Okay. And just pretty much fall? Because it's lost all its speed at that point? So which direction would you rather point the ball?
Left.
Down. When we point it slightly
Out
lower
or
so
up?
that out.
Out. And that's why. All right? You want to get it as far out as possible before it just kind of runs out of steam. Before air drag just makes it lose all its energy. Does that make sense? All right. And that doesn't mean shoot it horizontally, because if you shoot it horizontally, it's not going to leave the ground. And it doesn't mean shoot at 45 degrees because, well, we just explained that. So it's got to be something in between horizontal and 45. And what angle is that? Depends on the amount of air drag. Exactly right. There's very little air, then you can shoot it closer to 45. If there's a whole lot of air drag, then maybe you want to shoot at something a little lower. Anyone ever watch football? Anyone ever watch the angle that the place kicker kicks the football? Watch sometime.
Will depend on what he's going for.
Right, it does depend on what he's going for. But in particular, the most interesting case is a long-range kick. All right, watch for the angle. So, anyway, that's all I have.